Welcome Algebra 2A students to our first asynchronous session. Today I'm going to cover selected topics in Unit 1. Those topics include interval notations, simplifying radicals, simplifying expressions involving polynomials and expressions that involve exponents, and evaluating functions. If you need help on topics in Unit 1 not covered here, please feel free to contact me via email or the course messenger or through the telephone, and I'll be glad to help you. I want you to think of me as your best resource in this class. In order for you to succeed, your best chance of doing that is through reaching out to me. Now let's get to the topic at hand. All right, interval notation. We use the parentheses to indicate that we are talking about something that is strictly less or strictly greater than something else, meaning we don't want to include those numbers. We also use them for positive and negative infinity. So just to recap, we exclude an endpoint from an interval with a parenthesis. Now the brackets are used to indicate either less than or equal to or greater than or equal to, and we use that to indicate that we want to include that endpoint in the interval. All right. So let's talk about parentheses. Whenever something's going on forever to infinity, you always use the parentheses. That's because you can't include the endpoint infinity, because infinity isn't a number that you can point to on a number line, right? It's a concept. All right, so let's give some examples of how to use both this kind of interval notation. First, when you're graphing an inequality, we need to decide which kind of circle to use. Right? An open circle is used to indicate either less than or greater than, while we used a closed circle to indicate less than or equal to or greater than or equal to. Next, you decide which way you have to shade. All right, so if it's less than or equal to, we shade it to the left. And if it's greater than or equal to, we shade it to the right. So let's use the interval notation to represent the set of numbers indicated here. All right? Typically we would say, hey, this is x is greater than 3, but not including 3. Any number strictly greater than 3. All right, so to write that in interval notation, we have to use a parenthesis for the 3 because we're not including the 3 because it's not shaded, and then going on to infinity forever to the right, which we also always use a parenthesis for infinity. How about this one? I'll give you a moment to think about it. Let's indicate what this inequality is representing using interval notation. Well, this time we can see that we have a filled-in circle. All right? That means we want to include -2 as part of our answer. All right? When we want to do that, that's when you use a bracket. All right? So we're going to say, hey, it goes all the way from -infinity this way. So we use the parenthesis, and all the way up to 2 and including 2. So we use the bracket. We'll also use these later in your other lessons to define domain and range for functions. So you'll see this interval-like notation used again. All right, how about representing these set of numbers using interval notation? You can see that we say we want to go from -7, but not including -7, all the way up to and including 5. All right, so writing that using our typical notation, we would say that -7 is less than x, which is less than or equal to 5. The way I like to think of these is a range when you're using it, when you're indicating this as -7 being a low and 5 being the high point with x in the middle. In interval notation, we would say we go from -7, parentheses, because we're not including -7, up to and including 5, so we close it off with a bracket. Right, now I took this one from Lesson 1, Activity 6. All right. Use interval notation to represent the set of numbers x such that the following is true. X is less than or equal to 2, or 3 is less than x, which is less than or equal to 11. All right. So we're going to use both the brackets to indicate less than or equal to or greater than or equal to, and parentheses for less than and greater than. Remember, for negative infinity and positive infinities, we always have to use the parentheses, right? Because that is not a number that we can include, because it's not a number, it's a concept. All right, so to indicate this term here, x is less than or equal to 2, we're going to use the parentheses again and say negative infinity, comma, up to 2, and close it with a bracket. So it goes from anything less than or equal to 2, or negative infinity all the way up to and including 2. Next, we have to indicate this inequality, which we call a compound inequality. And if it's written with the word or, we have to include the word or, and we're going to go from 3, but not including 3, all the way up to 11 and including 11. All right, so let's talk about simplifying radicals. And I'm going to do it a little bit differently than they did in the lesson. All right, but let's talk about first what perfect squares are. We know that perfect squares are numbers like 1, 4, 9, 16, 25. That's because 4 is the same as 2 times 2. Or we can say that the square root of 4 is 2. So here I've listed the perfect squares all the way up to 144. Likewise, I can list the perfect square roots. So the square root of 1 is 1, the square root of 4 is 2, and so on, all the way up to 12. Now, in your lesson, they wanted to give you this list of perfect squares so that you could use that to then simplify radicals. But I'd like to show you a way to simplify radicals later that don't involve using perfect squares. But what we are going to use perfect squares for is to estimate the value of a square root without a calculator. All right, so in this example, we want to find two consecutive whole numbers that lie between the square root of 58 lies between them. In other words, I'm asking you, hey, what number times its own self is equal to 58? Right? That's what we want to try to find out approximately. All right. So we're going to go ahead and look at the list and see where the square root of 58 would fall in between. All right, so here's our list again of perfect squares. And we can see that the square root of 58 is in between the square root of 49 and the square root of 64. All right? So as whole numbers, we know that the square root of 49 is 7 and the square root of 64 is 8. So I know that the square root of 58 is somewhere between 7 and 8 as a whole number, right? Those two whole numbers. So let's go ahead and let's see if we can get this value then to the nearest tenth, one decimal place. All right, so here I'm listing that it's square root of 58 is between the square root of 49 and square root of 64, which we know is 7 and 8, somewhere between 7 and 8. I'm going to go ahead and look at the difference between 49 and 58, and they're 9 apart. And if I look at the distance between 58 and 64, it's 6. It's a smaller number, so I'm guessing that the square root of 58 is a little bit closer to the square root of 64, which is 8, than it is the square root of 49, which is 7. So we know this number is between 7 and 8, and now I know it's a little bit closer to 8 than it is to 7. And here's where you have to do a little bit of trial and error. So I'm going to guess. If it was right in the middle, right, that would be 7.5. So I know this is a little bit more than that because it's closer to 8, right, than it is to 7. So I'm going to go ahead and guess 7.6. So remember, what we're trying to do here is find a number that when I multiply it by its own self is 58. So I'm going to go ahead and square 7.6. And I see that I get 57.76 when I do that. All right, well, we want that number to be 58, right? That would be exact. So we're a little bit too low. All right, so I'll guess a little bit higher. How about 7.7 then? All right, so I'm going to take 7.7 and square it. When I do that, I get 59.29, right? Because that's a little too high. Remember, we want it to be 58. Now, since we're rounding to the nearest tenth, our job is to find out which one of these is actually, which number is closer to 58. Is it 57.76 or is it 59.29? And to do that, I'm just going to go ahead and subtract 58. It's 57.76, and I get 0.24. I'm going to go ahead and I'm going to subtract 59.29 and our 58, and I get 1.29. And that's how I know that, yes, 57.76 is closer to 58 than 59.29 is. Therefore, if I was asked to round this to the nearest tenth, I would say that the square root of 58 is 7.6, approximately rounded to the nearest tenth. All right, so I'm going to give you a moment to pause the video and try to estimate the square root of 115 to the nearest tenth. All right, so what you should have been doing is you should have been going through your list of perfect squares. You would have realized that 10 times 10 is 100. So we have the square root of 100. And 11 times 11 is 121. And so the square root of 115 is somewhere between the square root of 100 and 121. Or as whole numbers, right, somewhere in between 10 and 11. So now I need to find a good place to guess, So remember, if it was right in the middle between them, I would guess 10.5. But to see which one is closer to, I'm going to go ahead and subtract the difference. Well, 115 is 15 away from 100. How far away is it from 121? Well, it's only 6 away. So now I know that the square root of 115 is closer to the whole number 11 than it is to 10. So I'm just using that information to help me make a good educated guess about where I think this number is. So remember, if it was right in the middle, I would guess 10.5. So I know that this number is a little bit bigger than 10.5. Right? So maybe I guess, how about 10.7? All right. So 10.7 times 10.7 is 114.49. Pretty close to 115 that we want. It's a little bit too low. All right, so I'll guess 1/10 higher. So I guess 10.8. And 10.8 times 10.8 is 116.64. And again, we're trying to decide which one of those numbers is closest to 115. So we go ahead and subtract. We see that 114.49 is only 0.51 away from 115, while 116.64 is 1.64 higher than 115. So now we know that the guess of 10.7 was closer than 10.8. And so we know that this answer here is going to be 10.7 rounded to the nearest tenth. Somebody might be asking, why didn't you guess, after I guessed 10.7, why not guess 10.6? Well, the answer is, if we know that 10.7 squared is 115 and that's already too low, why would I guess a number that's lower than that? Right? I have to guess a number that's higher than that until you zero in on it. Let's say I had a question that asked me to estimate something to the nearest hundredth, meaning I want to go 2 decimal places after. Well, what I would do here is I would guess 10.7, this is like saying 10.70. Okay, it's a little low. Then my next guess after that, I might try 10.72. See how close I can get to that. If that's too low, I keep playing the same game back and forth until I zero in on a number. That's as close to 115 as I can get it, to as many specified decimals as we've been asked. All right, now as I promised earlier, let's talk about simplifying radicals. All right, so in the textbook, it's what they would have told you to do here is, let me grab my pen, is to go ahead and write out the square root of 50 using perfect squares. So you kind of have to have this list of perfect squares in your mind. You would have to know that, hey, the 2 times 25 is 50, and 25 is a perfect square. So they would have you rewrite this as the square root of 2 multiplied by the square root of 25. And then since the square root of 25 is 5, we could say that this simplifies as 5 radical 2. All right. I'm going to show you a different way using prime factorizations to do the same thing, and I'll tell you why we want to do it that way. All right, so let's go ahead and take 50 and break it down like how you've been shown in the past using factor trees. So I'm trying to think of any two numbers at all that multiply to 50. All right, so I'm going to go ahead and use 2 and 25. You could have used 5 and 10. It would make no difference. You would still get to the same factor tree in the end. All right, so I did 2 times 25. 2 is a prime number. 2 is prime because the only things that multiply to give me 2 are 1 and 2. So once we get to a number like that, we stop. However, 25 is not prime. In fact, 25 is 5 times 5, so I go ahead and use its factor tree, 5 times 5. And now again, 5 is prime because only 1 times 5 is 5. That's when we stop on our tree, when we can't go any further. All right, so 2 times 5 is 50, and 2 and 5 are our prime numbers. So we're going to go ahead and use that to rewrite the square root of 50 as the square root of 2 times 5 times 5. All right, because I haven't changed anything here, right? This number under here is still 50, which is what we started with. Now is what you're doing when you have a square root, is you're looking for any pairs of numbers that you can find underneath the radical. In this case, we have a pair of 5s. So I'm going to grab the pair of 5s, I'm going to pull one of them outside the radical, and the other goes away. Okay, so I have a pair of 5s, so I can pull a 5 outside of the radical, and that leaves me only in the 2 underneath. So that's what I'm indicating here with this arrow, that because of this pair, I'm going to pull one 5 out. The only thing that I had left underneath the radical was 2. So this is 5 radical 2. Same answer we got used doing it the other way. So let's do it again with this one, the square root of 48. So remember, the first thing we do is we're going to break down 48 using our factor tree. So I'm thinking of any two numbers that multiply to 48. You could say 6 and 8, but I'm going to go ahead and say, hey, 2 and 24. I know it's an even number, so I know I can divide it by 2. So if you're having a hard time figuring out what divides it, just start going through and get your calculator and say, can I divide it by 2? Can I divide it by 3? Can I divide it by 5? So you find things that multiply to give you 48. All right, 2 is prime, but 24 we can break down. So I'm guessing any two numbers that multiply to 24. So I'm going to go ahead and use 2 and 12. Again, you could have used 3 and 8, you could have used 6 and 4, whatever two numbers multiply to 24. 12 I'm going to break down as 2 times 6, and finally 6 breaks down as 2 times 3. Our prime numbers here are at the end of our trees. So 48 is the same as 2 times 2 times 2 times 2 times 3. And indeed, if you multiply those all together, you will get 48. All right, now just like before, we're looking for pairs underneath the radical, wherever I can group a pair. So I have a pair of 2's here, and I have a pair of 2's here. So from each of these pairs, I can rip out 1, 2 outside of the radical. Right, so here I'm indicating I'm crossing out the extra 2, and I'm pulling both of these, one pair, 2 out from this pair, and 2 out from this pair. So on the outside I have actually a 2 times another 2. You multiply those outside numbers. And what's left in the radical is the 3. And then we're going to go ahead and simplify and say on the outside 2 times 2 is 4. So what advantage does this have besides not having to memorize perfect squares? Now let me give you an example here real quick. Suppose I wanted to simplify the cubed root of 120. All right, so doing it the other way would force me to have this list of perfect cubes memorized. Well, I really don't. And if it asked me to the 4th root or the 5th root, that would even be harder. I don't have those numbers in my head. But this way, using this prime factorization method, we don't have to have those numbers in our head. We can do it the same way every time. So I'm going to go ahead and take 120 and I'm going to do its little factor tree. So again, I could think of any 2 numbers that multiply to 120. I'm going to go ahead and use 2 times 60. Number 2 is prime. All right? So I'm going to go ahead and circle it. Now 60 is not a prime number, so I'm going to break it down. You could say 6 times 10, or you could say 2 times 30, or any other combination that multiply to 60. I'm going to use 2 times 30. All right, 2 is prime. 30 will break down. I'm going to say 2 times 15. And 15 finally will break down as 3 times 5. All right, so the cubed root of 120 is equal to the cubed root of 2 times 2 times 2 times 3 times 5. I'm going to write that underneath here. 2 times 2 times 2 times 3 times 5. And the beauty about this method is, hey, now the number out here, the index, what we call on the radicand, this 3, tells me that I'm not looking for pairs this time or 2 of a kind, I'm looking for 3 of a kind. All right, so I'm going to go ahead and see that I have a 3 of a kind of 2's right here. All right, so from that 3 of a kind of 2's, I pull 1, 2 outside of the radical. Let me change my pen color here. Pull 1, 2 out from right there. And then I don't have any other triples, 3 of a kinds that I can make. Right? So I have the cubed root, and what's left underneath the radical is 3 times 5, which is 15. And we're done. All right, so the cubed root of 120 simplifies as 2 times the cubed root of 15. All right, and that's why I prefer this method. If this was a 4th root, we'd be looking for 4 of a kind. If it was a 5th root, we'd be looking for 5 of a kind. All right, I'm going to go ahead and erase this. So moving on to evaluating expressions. All right, an evaluating expression is just a process which we substitute numbers in to replace variables, and then we calculate the result using the order of operations. All right? So that's what I said there. Substitute a number in for the variable and then simplify. All right? And you got to make sure you use the order of operations. We plug in the numbers assigned to each variable, and then we use the order of operations to get our answer. That's what I refer to, if you see me refer to in your notes, as plug and chug. That's what I mean. You substitute in values and you use order of operations to work it out. In math, we refer to that often as plug and chug. All right, so let's evaluate the following expression for x is 3, y is equal to 4, and z is equal to 2. So again, wherever I see an x, I'm going to plug in a 3. Wherever I see a y, I'm going to replace that with a 4. Wherever I see a z, I'm going to replace that with the number 2, like I've done here. Now we have to use the order of operations to simplify. The order of operations, PEMDAS, tells me that I need to do exponents before I do multiplying. So I'm going to go ahead and square this 3 and take this 2 and raise it to the third power, or cube it. All right. So as we see, 3 to the second power, or 3 times 3 is 9. And 2 to the third power is 8, not 6, right? Because we're looking for 2 times 2 times 2. 2 times 2 is 4, times 2 again is 8. Now finally I can multiply across on top and bottom. So I did 4 times 9 times 4 and I got 144. And 3 times 8 was 24. Yes, you can cross cancel if you want to do that. In the sake of this video, to not overcomplicate it, I just multiply it across. But you could have told me that 3 will go into 9 3 times and 4 will go into 8 2 times if you wanted to simplify these numbers. So I multiplied across here and got 144. 3 times 8 is 24. And finally, 144 divided by 24 is 6. All right, so let's practice simplifying a polynomial. Again, we're going to let, in this case, x equal 2 and y equal 5. So wherever I see an x, I'm going to replace it with 2. Wherever I see a y, I'm going to replace it with 5. And you should get in the habit, just to make it a little more clear, when you substitute things in, to go ahead and put them in parentheses. All right, so I went ahead and did that. I replaced the x's with 2's and the y's with 5. Now let's use the order of operations. So what step should we do next? That's right, we should use our raise things. Exponents come before multiplying, so I'm going to do all the exponents. So I get that 4 times 5 here, and I get 5 squared is 25. All right, next, we need to do all the multiplication before we can do addition and subtraction. So there's all our multiplication. And this is 4 times 5 is 20. I think of this as negative 2 times 25, which is negative 50. And here 3 times 5 is 50. And then the last step is just to subtract from left to right. So 20 minus 50 is negative 30 plus 15, and negative 30 plus 15 is negative 15. All right, so let's evaluate this function. So we have that f of x is equal to 4x squared minus 84. And the question is, find f of 5. All right, I saw this in one of your lessons. I think it's lesson 4. Well, this is the same thing as saying, let x equal 5. It's no different than what we were just doing on the previous slide. So it's saying, well, hey, wherever I see the variable x, which is indicated here in this f of x, just go ahead and substitute in, replace it with 5. And then you'll notice we do the exact same thing that we here just done. I'm going to use the order of operations and say that 5 squared is 25. 4 times 25 is 100 minus 84, which is 16. All right. Now let's talk about simplifying expressions. All right. We're going to simplify expressions involving polynomials first. The way that we do that is by combining like terms. You know, like terms are terms that have the same variable and exponent. So here's an example of a term. The number in front is called the coefficient. All right, and here the variable is x. It doesn't have to be x. It can be any other letter or symbol. And the exponent on this variable is, in this case, a 2. All right. When you don't have a number in front of the variable, it's an implied 1. It's automatically a 1. All right, so let's go ahead and subtract this polynomial. Your first step is you're going to want to remove those parentheses. So notice that we don't see the 1 here, right? But there's an implied negative 1. So to get rid of these parentheses here, I have to distribute that minus sign, or I have to distribute a negative 1 to both of these terms. All right, so negative 1 times x squared and negative 1 times negative x. So negative 1 times negative x squared, you can see is, sorry, negative 1 times x squared is negative x squared, but negative 1 times negative x is positive x. And so watch your signs. Now we're just looking to combine like terms. So wherever I see a squared term, an x squared term, I combine it with another x squared term, or an x term with another x term. In order to combine them, remember they have to have the exact same variables to the same power. So here, those two are like terms. So remember, when we don't have a number in front as a coefficient, it is an implied 1. And then I just add or subtract the coefficients as we normally would. So I'm thinking 2x squared minus 1x squared just leaves me with 1x squared, or x squared. We don't write the 1 typically because it's implied. Next we have a negative x and a positive x. So it's like saying minus 1 and plus 1. So a minus 1x and a plus 1x is, well, 0 x's. So that term cancels out. Finally, we have the number negative 1, and there are no other numbers to combine it with, so I just leave it. Again, 0 times anything in this case is 0, so we don't write it included in our answer. Alright, so go ahead and pause your video and see if you can simplify this expression. Alright, so the first thing we want to do is get rid of parentheses. In this case, in order to do that, we need to distribute this negative 3 to all the terms inside. So we get negative 6x, positive 3xy, because there's a negative times a negative. And then we're going to get negative 9y minus 11xy. Right, now we're trying to combine like terms. Alright, so I look and now I see this first term here is just an x to the first power. Then I'm looking at all my other terms. I'm looking for one that just has an x in it, but I don't see any. So I just bring it down, negative 6x. Notice this next term is an xy term, and I have another term that involves both x and y, same variables to the same power. So now I just add or subtract the coefficients, and we're thinking to ourselves, what is 3 minus 11? Well, 3 minus 11 is negative 8, and then I include the term xy. Then finally we have this last term here that we haven't done anything with, this negative 9y. So I'd be looking for any other y term out here that I can combine it with, but there isn't any. So I just bring it down. Next we're going to talk about simplified exponents, expressions that involve exponents. And there's 5 basic rules that you need to know in order to do that. 4 used most, and I'll talk about the 5th later, is 1, the product rule for exponents. That's when we have numbers with the same base but different exponents. We keep the base the same and we add the exponents. So in this example down here, x squared multiplied by x cubed, I just add the exponents to get x to the 5th power. Let me demonstrate why we do that. Alright, so x squared really means x times x. We're going to go ahead and multiply that by x cubed, which means, well, 3 x's multiplied by each other. X times x times x. Now you can easily see that we have 5 total x's being multiplied by themselves, and that's what x raised to the 5th power means. So that's the first rule we need to know. The next one we're going to talk about is called the quotient rule for exponents. So when we're dividing 2 exponents, like in a fraction, they have to, with the same base, we subtract the exponents. So when we're multiplying and we add, when we're dividing, we subtract. But remember, this b and this b on bottom, that means whatever that base is has to be the same. So if it's an x up here and a y down here, you can't subtract those because they have different bases. They have to have the same base. Alright? So the example down here is x to the 7th divided by x to the 3rd is equal to x to the 4th. And again, I can demonstrate that if I wanted to by writing out 7x's on top and 3x's on bottom. And 3x's are going to cancel with 3 of the x's on top, and that would just leave you with 4x's being multiplied on top. The third one is the power rule from exponents. So when we take an exponent like this, right, that's being raised to some, a base being raised to some power, then we raise that to a power. All we do is we multiply the exponents. That's what that means here. So when we're raising a power to a power, you multiply that exponent. So x cubed taken to the 4th power is x to the 12th power. And the reason why, how I can demonstrate that, is that here we have 3x's being multiplied by each other inside the parentheses. That would be x times x times x. Then if I raise that to the 4th power, it indicates that I have 4 sets of those. So I have 4 groups of 3 x's. That would make a total of 12 x's being multiplied by each other. And then finally, when we have negative exponents, like say x to the negative 4, 2 to the negative 4, whatever it is, you can replace it, switch it, think of it as a fraction, and put it as a positive exponent in the denominator, or vice versa. If you had a negative exponent in the denominator of a fraction, you can move it to the numerator of a fraction and make it positive. That might make more sense when I do a few examples. All right, so let's simplify this expression here. Right, is what I'm going to go ahead and do first. Right, is I'm going to get rid of this. I'm going to go ahead and apply the power rule for exponents first. So I want to get rid of this being raised to the negative 3rd power, all that. So is what I do is everything, every single base inside those parentheses, I multiply the exponents together. So I got x to the negative 6 in here because I went 2 times negative 3 is negative 6. The x. Then remember, we don't see a 1 up here on the y, but there's an implied 1. So I went 1 times negative 3 is negative 3. The 4 was outside of the parentheses. I wasn't raising the 4 to the negative 3rd power, just the stuff inside these parentheses. That's the base. All right, and I left the bottom the same. All right, so let's simplify from here. So is what I did to get from step 1 here to step 2 is I went and I applied that quotient rule. So I looked on top and bottom and I saw things with the same base. So as here I noticed that I have x on top and I have another x on bottom, and I have a y on top and I have a y on bottom. So the rule states that I should subtract those. All right. So as what I did is I said, well, I went negative 6, I'm going to take x, and the rule says subtract the exponent, so I went negative 6 minus 4. And that is how I got x to the negative 10 right here. And I'm going to go ahead and do the same for y. So I have y to the negative 3rd power, and I'm going to subtract negative 3 and 1. And that's how we get that y to the negative 4th power right here. Finally, though, we don't like to leave expressions with negative exponents in it. That's not considered simplified. So we're going to go ahead and use our 4th rule, right? And wherever we have negative exponents, I switch them in the fraction. So if I have a negative exponent in the numerator here, notice I threw it down in the denominator of the fraction and made it positive. And I did the same thing with y because it happened to be a negative up here. So I took the negative 4 and I moved it to the bottom and made it positive. There, now we have no more like bases that I can combine, no negative exponents. I can't simplify this 4 over 3 any, they don't divide, so we're done. All right, so how about we simplify this exponent? I'm going to give you a moment to try. All right, so remember first, I like to apply the product rule. I want to get rid of all this stuff raised to the 2nd power, this entire group on the top. All right, this entire group on the top is being raised to the second power. And the rule says I multiply the exponents, and that's every single exponent up there. All right, so I'm going to go ahead. Okay, so it's what I did to get from step 1 here to step 2. Because I went ahead and said, look here, we have the same base, x and x. Here we have an x squared and an x to the negative 4. When we have same bases multiplied together, we add exponents. So I went x and 2 minus 4 is negative 2. All right, so then we still had all that raised to the second power. Now I went ahead and applied the power rule. And I multiplied that 2 by all the exponents up there. So even and applied 1 on the numbers even. This is 3 to the first power. So I went 1 times 2 is 2. Then negative 2 times 2 is 4, and then here's the 1 again, and 1 times 2 is 2. All right, so now I've applied the power rule, and we have no more parentheses. All right, so now I'm going to go ahead and apply the quotient rule on top and bottom. Right? So we said that 3 squared is 9. Right? And now we're going to go ahead and say x to the negative 4 minus 3 is negative 7. And I write that all in the top at first. That's my preference. And then I like to switch them around if they're negative at the end. Finally, here I get 2 y squared and a y to the being divided by y to the negative 4. So I go 2 minus a minus 4, like this. So be careful with that. So follow your rules of addition and subtraction. Here I have a 2, and I'm going to subtract it because we always subtract the exponents. The bottom exponent happened to be a negative 4. So that's the same as saying 2 plus 4, which is positive 6. That's how I got y to the positive 6 on top. And then finally, we don't like to leave negative exponents. So I'm going to take this x to the negative 7, and I'm going to throw it in the denominator of the fraction. That's all I did. I moved it from the numerator here to the denominator there. And then if I could divide 9 and 2, I would. Or if I could simplify them like I would simplify fractions, I would. But in this case, I can't. All right, so now I'm going to go ahead and send out this to you guys via your course messenger and also on my announcements. And there are 5 questions. Answer the 5 questions and then email it back to me or send it back to me through Messenger. Again, if you have any questions, you can email me, contact me through Messenger, or contact me through the phone, Monday through Friday, 8 to 5.